This is Larry Benko, W0QE, and this video is about transmission line voltages and currents. However, before we begin, I'd like to take a small detour and talk about the Splat. It was brought to my attention and I ignored the Splat in video number 2 where it should have been introduced. The Splat is this thing right here. It can be moved around the Smith chart at will. It can actually be moved outside the Smith chart if you wish. It indicates the impedance that point represents. So think of it as a digital display on what is shown in the Smith chart. The Smith chart has guidelines that would help you out to what the actual value is. So if I put the Splat right there, I can see that resistance is 50 ohms here. Resistance is 100 ohms here, so maybe that's about 60, 65 ohms. I can see that the reactance is 50 ohms here, 100 ohms there, so maybe it's about 60 again. 60 plus 60. It's not real accurate to do, to interpolate visually, but you can kind of get close. This gives you a very, very good way to get very accurate representation of what the impedance is. Likewise, it also will give you the value of admittance. Admittance and impedance are very closely tied together. If you look at Wikipedia, says that impedance is defined with 3 lines here, defined as being 1 divided by impedance. Impedance is a complex number, therefore admittance is a complex number. And you might ask yourself, well, gee, if you know this one, if you know impedance, you know admittance, and the answer is yes. Impedance is an indication of how well current is resisted. Admittance is an indication of how well current's allowed to flow. So they're exactly opposite to each other. However, there's a good reason to have admittance, and that was in the days when we used to do stuff by hand. 2 components in series. If the 2 components are known by their impedance values, you just add them up. They're complex numbers, but you just add them up. You add the real parts of the 2 numbers and the complex parts of the 2 numbers, and you've got the answer. However, if the 2 components are in parallel, you had to do the old 1 over 1 over formula, where you're messing around with complex numbers, taking the inverse of them and stuff. And in the case of admittances, 2 components in parallel, the 2 admittances add. So if you convert from impedance to admittance beforehand, which is a fairly simple thing, it's a one-step kind of, it takes a little bit of math, but it's algebra. And then you just add the 2 admittances together, and you got the answer. Then you can take that number again and convert it back to an impedance because it's just 1 over that number. So a lot of times doing the problem by hand, it was more convenient to have admittances than it was impedances and sometimes during the problem. So let's look at the Smith chart here. This Smith chart, the pink lines represent impedances. The blue lines represent admittances. If we look at a more complicated Smith chart, one that would be a little more accurate than the rudimentary one that SimSmith gives us, where we actually had to figure out where a particular value was on the Smith chart, we have a lot more lines. We have lighter and darker ones, and you kind of can interpolate where you are pretty well. This is an impedance-only Smith chart. There are no admittance lines on here. To put admittance lines on here, you have to take all these lines, flip them left to right, and do them again. If you do them again, you need a different color. It gets to be incredibly complicated to do that visually, but that's what's needed to be done. However, in the case of SimSmith, it does all the math for us. So who cares? As a matter of fact, you don't even need these lines on here at all. Their guidelines are kind of cool. They give you indications as to when components are added and in parallel and series, the paths they the paths they will take. But other than that, you don't really need those lines. So if we click on a point right here, that point is exactly those coordinates. If we had a component in the circuit and we click near the component, nothing happens. However, if we click very near the component, it snaps to the path or the endpoint. In this case, it's a 50 ohm resistor, a 50 ohm reactance, 50 minus J50. Very, very easy to read the actual number off here. In this case, since it occurred on a line, it's not that hard to interpolate it. But let's go back and put our splat there. That's 85.0 minus J109 for impedance, or that admittance value. This displayed on here, which can be thought of as, like I said, a digital display of the analog Smith chart, has 4 pages of data. This is page 1. Page 2 is an admittance-only page. The admittance-only page is not very exciting except for this one line right here. This tells us that this point right here is equivalent to 224 ohms in parallel with 90.8086 picofarads of capacitance at 10 megahertz. Click again. We get an impedance-only page. This page tells us that same point is equivalent to 85.0 ohms in series with 146.6 picofarads, again at 10 megahertz only. So that point can be represented with those 2 component sets if you wanted to actually implement it for some reason. The 4th page is a chart coordinate page only, with the Smith chart being defined as XY coordinates both in a rectangular format and a polar coordinate format. This point right here represents a reflection coefficient of 0.658. So if this is 0, it's 0.658 of the way out to the edge at an angle of 33 degrees, minus 33 degrees. One more click, we're back to where we started. This point here also represents an SWR of 4.853. We just went over what gamma was. And like we said before, the impedance and admittance. That's pretty much all a splat does. It stays put. It doesn't move. However, if you zoom in and zoom out, it stays put. But if you click to pan, it will move. And that's just because you pan by pushing the left mouse button down, and the left mouse button moves the splat before you can actually drag it. So if you want to keep the splat in a known location, you should have the Smith chart oriented the way you want it to begin with. However, I can zoom in and zoom out by rolling the scroll wheel and not affect the location of the splat. That's pretty much all I wanted to say about the splat. There are several ways we can use SimSmith to demonstrate the voltage and current along a transmission line that has SWR. And whatever way I probably do, there'll probably be someone that can suggest a better way to do it. But nevertheless, I'm going to try to do it in a way that I think is straightforward and obvious, hopefully, and still introduce a few new features of SimSmith along the way. So let's start off with we can do this at 10 megahertz, that's fine. And we're going to start off by adding a piece of transmission line. Now we don't see much action here if it's 50 ohm line with a 50 ohm load. So let's give it a 2-to-1 SWR to start with. Click right here with the splat, 2-to-1 SWR. And let's make the length of this cable long enough to do a full revolution. Notice the clockwise direction of rotation as we increase line length. Let's see, make it maybe 33 feet. Now, the reason this circle does not line up with the starting point is due to the loss in the line. And that's typical of all transmission lines that have loss. Well, all transmission lines have loss, unless we play some games to make it a non-real line. There's a line with no loss. Notice it lines up right on top of itself again. So let's go back to the case where it had the loss. This piece of transmission line is a simplified model. It has loss. It has lots of, typical values, I guess, in it. 0.5 dB per 100 feet is approximately RG8 type loss characteristics. So nevertheless, let's use this as an example. What I'm going to do is I'm going to create 2 more pieces of transmission line. Click on that one, Control C, Control V, copy it, Control V again, copy it one more time. Now let's introduce using an N block as a control to set the lengths of these lines. What I want to make is a little line that's small, and I want to be able to move it around in this sea of 3 transmission lines, and hopefully this should become obvious in just a moment. Let's look at the end block here. The end block contains a do-nothing set of 3 lines. We have a port 1, which is comprised of a W1 terminal and ground. You can name those anything you want. Port 2, which is comprised of a W2 terminal and ground. Ground connects to ground, and a 0 ohm resistor called R0 that connects W1 and W2. Obviously, this circuit does nothing. In that case, it's just basically 2 wires that go straight through. However, we can also do some other things. And let me start, and I'll try to explain it as I'm going along. We'll take transmission line number 1, which is this one. We'll take the parameter FT, which is the length of the transmission line, and we'll set that equal to some new variable called length. And as soon as I type LEN appears here. And this, we will put a value in here later. Now, transmission line 2, it also has a parameter called FT, which is its length. And we're going to set that to be a constant value of 0.5 feet. And finally, transmission line 3, it has a parameter called feet, which is its length also. And we're going to set it to be a new variable called total. That's the total feet. We'll make that 33 minus the length from up above minus 0.5. Oops. Minus 0.5 feet. So whatever length this is, and this is 0.5 feet beyond that, and this is the residual up to 33 feet. So the sum total of all 3 of these is 33 feet all the time. But this point can be moved around. So, and we don't see much action here for the very simple reason that we haven't specified a total length yet. And let's set this to be, I'll right click on this in this parameter here, and I'll set it to be arithmetic. Values always default in SimSmith to be geometric, which is much nicer most of the time. But if we know we want to control things in a nice linear fashion, we can set these to be linear, and we can set whatever value we want them to be. So that's a 0.5 foot step. So if I click over here and I start scrolling my mouse wheel, I basically can add length to my circuit. Now, it's a little tricky to see what's going on down here. So let's see if we can come up with some better colors that'll show a little bit better. Let's make this one black. Let's make this one a little bit lighter color, green, perhaps. And we'll make this one maybe a lighter color, I don't know, pink or something. Okay, this is the black segment, is the 1/2 foot segment. And as I move this around, this variable, I can make that 1/2 foot segment vary anywhere I want along the length of the total transmission line. And if I start at the beginning and I want to look at this transmission line, I can see the voltage and the current and the power consumed in it. Now, we need to do a couple things before we can really run this properly. If we want to know how much loss is in the transmission line, we need to make sure that our generator puts all of its power into the transmission line. The generator that's the default generator here is a UZ0, which only puts maximum power, its maximum power in when there's a 50 ohm load here. Well, there's clearly not a 50 ohm load here. We can see it, it's a 100 ohm load. It's right there. The blue X in the blue component, it's a slightly capacitive, but it's probably let's look at it. It's 97.2 minus J2.86. So let's change the generator type. If we change the generator type to an X match, what that means is it's a generator that's capable of putting out 1 watt, but there's a mathematical matching network here that will guarantee 1 watt goes out no matter what the impedance is out here. So if you remember from an earlier video, when the arrow on the watts designation here is pointing to the left. That's the power delivered into the right-hand side of each of the components. So 1 watt is delivered into here, 0.9545 watts is delivered there, 0.9542 watts is delivered there, etc., etc. And the reason, of course, that this is a small difference between this one and this one is because this is only a 0.5 foot long piece of transmission line. So we can go and we could scroll around here and do all kinds of stuff and look at the loss here and look at the loss elsewhere. But let's just real quickly look at it and see what's going on. The voltages are pretty small here. They're kind of hard to remember. So let's go back here and let's up the power. Upping the power doesn't really change anything. It just scales everything to a number that maybe is a little bit more, you know, maybe it's more readable or more rememberable. How about that? So let's change the power now to be this way. This is the power now consumed in each one of these pieces of transmission line. If you had a 1,000 watt generator that was matched to this line, you would generate 45 watts of heat in this line. You would generate 0.3 watts of heat in that short little piece, and no power in this one because it's no length. We have the black sections at the very beginning, so there is no T1 effectively, delivering 954.2 watts into the load. And as we move the little segment around, the piece of transmission line, the 3 pieces together don't really change. It's just where this one sits within that group. So let's move this one. Now, if we notice this one before we move it, it's 0.3 watts, it's 308 volts, and it's 3.1 amps. If we move it to the other side here, we have 157 volts, which is about half of what the voltage was here. We have 6.2 amps, which is twice what the current was over here. This current right here is twice of what was over here. And our power is 1.06. Our power is considerably higher than our power was over here in terms of the loss. And we can show that a lot of different ways, but probably the best way to show it is to plot it. And we can plot that by the plot menu. The plot menu's a little bit, let's just say it's a little bit odd how it works, but once you get used to it, it's pretty clever. You're plotting variables that often are complex numbers, so you have to be a little bit careful. But the solution to that is basically just plot them as a magnitude. We're going to plot transmission line 2, and we're going to plot the power in transmission line 2, and it's a small p because if it was a large P, we'd be plotting the power coming into the line right here. We want the power consumed in there, so we're going to plot that, the power in transmission line 2, and what we're going to do with that power is we're going to put it on an axis called power. The square chart in SimSmith has 2 axes that are already defined when you start off. The power axis is on the left. The SWR axis is on the right on the square chart, and then there are 2 other axes that you can name as you wish and put whatever you want on them. And we'll put on, I'm going to have to call this magnitude in this one, in this case, because the voltage that I want to look at, capital V, is because it's the voltage I want from here to here. I don't want to know the voltage across the transmission line. I want to know the voltage from here to here, which is really across the line. I don't want to know it from end to end. I want to know it across the line. This is a complex number, this V, and I don't want to plot that. I can't plot that really. I want the magnitude of it. So I'm going to plot T2.V, and I'm going to plot it on a graph that I'm going to label volt, let's just say, and I'm going to use axes Y1. I'm going to plot again the same thing, except this time I'm going to plot the current. I, again capital I, because I want to know the current going into the part. In that case, I or small I would both be the same. Amp, and I'm going to use axis Y2. And hopefully this kind of makes sense. There's extra parameters here that I'm not including. They're in the documentation and the presenter documentation for SimSmith, and I'll do subsequent examples in other videos that will show this better. But this plotting is very, very powerful in SimSmith. So now I've plotted those. let's go over here, and I see frequency on the bottom here. I don't really want frequency on the bottom. What I want to plot on the bottom is the length of the I want to plot this variable as because that's the position of where things are happening. So what we plotted here right now with frequency is we've given this length right here where things appear as a function of frequency. We can add another sweep variable. We'll click on name, and we're going to click on the N1 is the component, N1 length, that variable. We're going to make that variable a variable we can sweep. We're going to turn it on, and we're going to sweep from 0 to 33 feet, and that is 67 segments if we do it in half-foot steps. And this is what we get. So let's look at this. Let me turn these off for a moment here, and let's look at the voltage first of all. The voltage goes on a plot here, and we see a peak of about 310 volts. I think we saw 308 before or something. We see a minimum of 150 something. It shows up here as 157, and that's about a 2-to-1 difference. That 2-to-1 difference, and this is back to the peak again. The 2-to-1 difference is a 2-to-1 SWR, and 100 ohms is a 2-to-1 SWR. And if we plot the current now, it'll be an axis over here. The current is now, excuse me, the red trace, and it will vary when the voltage is minimum, the current is maximum at about 6 point, we can look at it and see what it is. It's 6.2 amps. And down here where it's minimum, it's like 3.2. And down here it's 3.1 or something, probably 3.1. So we see a 2-to-1 variation in the current also. So there's again another 2-to-1 SWR indication. Now the final thing we're going to plot is power. This is the power consumed in each one of the little segments, and of course a smooth curve is drawn in between them. We see the power at this segment. It lines up with current because high current means higher power, because the power that we consume in the coax generally is proportional to the square of the current that flows. So from the peak power here, which is about 1.07 watts, to the minimum power, which is 0.31 watts, should be a factor of 4 different. Well, it's not 4 different because there's another loss in coax, and that's called dielectric loss, and this model obviously has dielectric loss in it also. We could change this model out to be a model that had no dielectric loss, and we would see a 4x difference in power. But that doesn't really change the value of this discussion. So if we look at this now for a moment and watch what goes on here, let me change this impedance to be a 3-to-1 SWR. Now we see the voltage going from 375 volts down to 128, just about 3-to-1. And we'll see the current going from 7.5 amps down to 2.5, about three times again, and the power varying between 1.56 watts now in that one segment, down to something like 0.27. And a 3-to-1 SWR should have been a 9-to-1 difference in power, but it's more like I think it's more like a 7-to-1 or 6-to-1 difference because of the dielectric losses are high when the voltage is high. The voltage is low here. The voltage is high here. The voltage is high here. So when the voltage is high, the dielectric losses are high. The current's low, so you don't see the disparity. The interesting thing is, though, if we look at the loss in the piece of transmission line when there's a 50 ohm load, we see the loss here, and this is just an artifact that the two of these just happen to be on top of each other. That's odd. I can get them off. You see a little bit of increase here in the current as we get our segment closer and closer to the generator. This small difference between this and this is the loss in the cable, the matched loss. The voltage drops a little bit too, and the power drops a little bit too as we consume a little bit of power. But the numbers are pretty flat. The power consumed with a 50 ohm load here is such that we get 962 watts of our 1,000 watts. 1,000 watts here, right there, to 962. So we see 37 37.3 watts is lost with a 50 ohm load. A 2 to 1 SWR drops this down to 954 watts. So it's 46 watts lost. A 200 ohm or 4 to 1 SWR drops this down to 925. A 10 to 1 SWR or 500 ohms drops this down to 839. We see increasing loss in the transmission line with increasing SWR. And of course, with a 10 to 1 SWR, we see some pretty wild voltages and some pretty wild currents. So in this case, a 10 to 1 SWR at 1,000 watts on RG8, we would see our voltage here is 650 volts RMS. Our current is 18 amps. 18 amps would do some serious damage on that poor piece of coax. That 1/2 foot section would have 4 watts of power in it in 1/2 foot. That's may not be enough to melt it, but it's enough to certainly warm it up quite a bit. And you can get a, I mean, you know, it is what it is. This is the way transmission lines work. So SimSmith does a very, very nice job of this. If you're used to seeing more than one cycle of this, we could easily have made this sweep go to say 60 feet, and it would have worked just fine. We see the repeating pattern. The power again is peaks when the current peaks, and when the voltage is a minimum. This is a pretty good. I don't know if this is the best way to demonstrate this in SimSmith or not. If you have some other suggestions, I'd be glad to do it and put them in a video. If someone has a better way that might show this more in a more clear fashion. But SimSmith does a really nice job of explaining this in a manner that's pretty easy to understand. And it may be a little bit difficult while I'm operating it and you're watching me to understand it. But if you play with it yourself, it's a lot simpler once you play with it a little bit, and get used to it. I'm going to leave this up here on the chart for a minute. If you want to copy these down and try to reproduce them or something, get it kind of out of the way or something. Anyways. I'll leave it up here on the row as I finish up. But basically, this is what happens in a transmission line, and the ability of SimSmith to graph and do these calculations is a very, very powerful tool. And I hope people appreciate the effort that Ward has put in on this program to make this a lot better than just a typical Smith chart program that can do matching on the Smith chart. It can do a lot of other things. One thing I might make note of here is these voltages and these currents are RMS values. If you're familiar with LT Spice, LT Spice reports peak values. And when you enter a voltage, you enter the peak value of the voltage, and you have to convert it to RMS, which it can do, of course. But SimSmith returns RMS values directly. So anyways, hope everyone enjoyed the video, and there'll be several more. Appreciate it again.